Hi, this is Jack from PhysiologyZone, and in this final episode on skeletal muscle, we'll be talking about the control of tone. So to do this, we'll cover four things: the motor unit, twitch contraction, quantal and frequency summation, and then finally look at the resting muscle tone and the movements which our muscles can create. Firstly, let's just begin by looking at the motor unit. So here on screen we have a familiar picture, which is the motor neuron made up of the axon, the myelin sheath, and the axon terminals. We also have the muscle fibers. Now, a motor unit is the number of muscle fibers which are innervated by one motor neuron. In this case, one motor neuron is innervating 3 muscle fibers. The importance of understanding what the motor unit is comes from being able to understand the functionality of why our muscles do what they do. So take, for example, one of the eye muscles, such as the lateral rectus muscle on the screen. These muscles around the eye have 10 to 15 muscle fibers supplied by one motor neuron. So that's quite a small size in terms of the motor unit. The small size of motor unit means there are a large number of motor units, and those two things together allow precision of movement, which is obviously important for the eye, and the same is true for muscles within the hand. Now, if you contrast that to a muscle such as a biceps muscle, there will be 1,000+ fibers, all stimulated by a single motor neuron. So the size of the motor unit is much bigger, and that means there is a smaller number of motor units. Those two things together give us much more gross movement. So that makes sense in terms of what we need those muscles to do. We need the eye to have precision of movement, but we don't need lots of power to be developed. So they're small muscles with lots and lots of motor units. Comparatively, the biceps muscle, or say the quadriceps muscle or the gastrocnemius muscle, well, they have much larger size of motor units, and they're much bigger muscles, and that allows them to develop lots of power but not have that precision of movement. So now that we understand how muscles are made up of motor units, let's just put this into context of how we develop movement within the muscle. So again, here's our motor neuron and our muscle fiber. So action potentials are always the same size. So when a motor neuron goes and synapses with a muscle fiber and a single action potential comes down that motor neuron, it will provide a single action potential into all the muscle fibers it supplies. In this case, it's just the one. This action potential is always the same size in any given neuron, in any given muscle fiber. This is called the all or none law. In contrast, the muscle fiber contraction in terms of speed and strength does vary, and the key things that determine this are the twitch contraction and quantal and frequency summation. So we'll begin by discussing the twitch contraction. This is the brief contraction of all the muscle fibers in a motor unit in response to a single action potential running down its motor neuron. So to explain this slightly clearer, let's consider this graphically. So on screen what we have is a graph that shows tension in the muscle fiber on the y-axis and the time in milliseconds on the x-axis. So let's consider what happens when a single stimulus, i.e. an action potential, stimulates a muscle fiber. So considering the event in its entirety over about 100 milliseconds, this is what happens. The tension increases in the muscle and then it decreases again, back down to a resting state. This whole event shows the muscle contracting and then relaxing, and we can break that into 3 parts. Firstly, the latent phase. So the muscle action potential sweeps across the sarcolemma and calcium ions are released from the sarcoplasmic reticulum into the sarcoplasm, and that whole process lasts somewhere in the region of 2 to 5 milliseconds. Then we get the contraction phase. In this period, calcium binds to troponin C. It reveals the myosin binding sites on actin, the cross bridges are formed, and that lasts about 10 to 100 milliseconds. And then finally, we have a relaxation phase, which is where the calcium is actively transported back into the sarcoplasmic reticulum. The myosin binding sites are covered by tropomyosin complex. The myosin then detaches from the actin, and the tension in the muscle fiber decreases. And that process lasts yet again about 10 to 100 milliseconds. It's also worth noting that during the initial 5 milliseconds approximately after the initial action potential, there is a refractory period in which a second stimulus will not cause a second contraction. I suppose it's easiest to think of that the muscle fiber is just too busy during this period to receive another action potential. That whole process on screen takes, on average, between 100 and 200 milliseconds, but it can be as quick as 20 milliseconds. And the speed at which this process occurs relates to the type of skeletal muscle fiber. So I'm going to quickly just introduce the 3 types of skeletal muscle fibers that we have. So we have slow oxidative fibers, which are also known as type 1 fibers. We have fast oxidative glycolytic fibers, which are known as type 2A fibers, and we have fast glycolytic fibers, also called type 2B fibers. So beginning with the slow oxidative fibers, the type 1 fibers, they're very small in size, so that causes them to have a weak contraction. They use oxygen and have lots of blood capillaries, so they're dark red. They have tons of mitochondria and lots of myoglobin to store that oxygen, and they generate their ATP by aerobic respiration. Because of that, they have little glycogen stores. And their twitch lasts the longest of all these 3 muscle fiber types, at about 200 milliseconds. So it's quite a slow process, but it's efficient. The importance of that is that they don't fatigue very easily. So it's this type of fiber that's predominantly seen in muscles that are involved in posture and are most utilized in activities such as marathons or walking very, very long distances. Next, we have the fast oxidative glycolytic fibers, the type 2A fibers. So these are intermediate in diameter, and because of that, they're quite strong. They use oxygen, so they have myoglobin, blood capillaries, and they look dark red because of that. Plus, they have mitochondria, so they do use aerobic respiration. But they also have glycogen stores and use glycolysis, so anaerobic respiration. So these type of fibers use both types of respiration. Their twitch lasts about 100 milliseconds, and so they're best utilized in something such as a 400 to 800 meter race. So they're quick at producing energy and reasonably efficient, but they do fatigue after some distance. Finally, we have the fast glycolytic fibers, the type 2B fibers. Now, these are very large in diameter, which makes them very strong in terms of contraction. They use glycolysis in terms of their respiration. So they have lots of glycogen stores, but there's no real need for oxygen. So they have little myoglobin and few capillaries, which makes them look much more white in comparison to the other 2 fiber types. Their twitch is the fastest of all 3, lasting about 50 milliseconds. So it's very fast in terms of the amount of energy it can produce and the power of contraction, but they have poor efficiency, meaning that they fatigue quickly. Now, of course, it would be quite wonderful if they would all fit quite snugly into this categorization, but the truth in reality is that this is kind of, if you will, a spectrum. So muscle fibers do not neatly fit into these categories, but they do have characteristics of these types. So there's quite a lot of overlap in reality. The speed of the twitch is the reason for their name, so slow and fast. And the speed is directly correlated with the enzyme ATPase, which is responsible for hydrolyzing the ATP on the myosin heads to ADP and an inorganic phosphate, which, as you remember, is required for forming the cross bridges with actin. The speed at which this ATPase enzyme works to do this is where its name is from. So in fast glycolytic fibers, the ATPase rapidly hydrolyzes the ATP to ADP and an inorganic phosphate. And again, this is where the classification breaks down, because in us, there are several different isomers of the ATPase, and they are all working at different rates. But for conceptualization purposes, it's best to categorize them into this format, but have that understanding that it, of course, is not this perfect. The reason I've brought this up is because that we're all genetically determined before birth in our muscles as to how much of one fiber type we have in comparison to another. And we also have different amounts of these fiber types in different muscles dependent upon what they're typically used for. So for instance, posture muscles like the back muscles have more slow twitch fibers. In the muscles like the biceps, we have more fast twitch fibers. And the genetic side of things, you'll know that some people are just excellent at running long distances, and others are very good at sprinting naturally. And the reason for this is because of the distribution of these fibers within the muscles in each individual person. Okay, now we're going to talk about quantile and frequency summation. Quantile summation simply refers to the number of motor units which are recruited and therefore the number of muscle fibers which are contracting. The way a muscle works is to first recruit the weakest motor units. So if you think about holding a glass of milk with a flexed elbow, it's not quite as difficult as if you were to try and hold a much heavier dumbbell in that same position. When you're holding just something quite as light as a glass of milk, there is low recruitment of motor units. As the weight increases, we recruit more and stronger motor units progressively. This is great because it means that our muscles don't fatigue too quickly, as when some motor units are on, some are off and so relaxed. And this allows us to change the force of the contraction, which therefore means we can have more precision in our movements. Frequency summation can be best explained using a myogram, which is what you can see on screen. On the y-axis we have tension, and on the x-axis we have the time, and this is all happening within a single muscle fiber. You'll remember that all muscles have that refractory period, which is where if a stimulus is applied during that time, they can't contract again. But after that period, they are ready to receive another stimulus. So, for example, if you applied a single stimulus to the muscle fiber, it peaks in terms of its tension. It has, during that first moment of contracting and building tension, that's the refractory period. You couldn't get it to contract again during that period. But now it's starting to relax and come down. It can receive another stimulus. If an action potential gets to the muscle fiber before it has completely relaxed, then the second contraction will be stronger. And that continues to happen up until a point when the muscle develops maximal tension. And in this myogram, we've just ended the number of action potentials being fired at the muscle. So it's now completely relaxed. And of course, this is possible to occur because the contraction and relaxation phases are much longer than the refractory period in the muscle. So as repeated action potentials hit the muscle before it relaxes, it gets stronger. And it looks graphically like a wave, and that's sometimes why it's referred to as wave summation. There are a couple of other important concepts with this same idea in mind. So we also have something called tetany. Now, tetany occurs when a motor unit has been maximally stimulated by its motor neuron. When a muscle is tetanized, the contracting tension in the muscle remains at a constant and steady state, and that's the maximal possible contraction. In tetany, there are actually two types. There's incomplete or unfused tetanus, and this is where you're effectively applying the stimulus in the form of the action potential about 30 times per second. So you're applying it an awful lot. And this is where the muscle fiber is producing maximal tension, but it is slightly relaxing in between the contractions. And you also have complete or fused tetanus, which is where if you were to stimulate it, say, 100 times per second, then the muscle fibers would produce maximal tension and they do not have time to relax at all. So on a myogram, it just looks like a straight horizontal line at maximal tension. The theory behind how this is all working is that an action potential is releasing calcium into the sarcoplasm, and that's causing the contraction. But almost instantaneously, calcium is leaving the muscle fiber and it's beginning to relax. If you hit it with another action potential, there's more calcium released into the sarcoplasm, increasing the amount of calcium that's present. So now the muscle fibers cross bridges, already partially activated, are activated for longer because there's more intracellular calcium, so they can form more cross bridges and thus develop more force. And with quicker and quicker action potentials, you get more force developed by the muscle fiber because it has time to create the cross bridges. And once all the cross bridges have been formed, you reach that maximal tension within the muscle fiber. Now, putting this into reality, in our body, sustained contraction of our skeletal muscles is generated by incomplete tetany, and that is occurring with what most believe is an asynchronous activation of our motor units, whereby the motor units which are relaxed begin to fire as the motor units which are contracted begin to relax, and they just cycle. So some are relaxed, some are contracted, and it just keeps spinning round. And you can see this through, if you, for instance, hold your hand out, you'll see that everybody has, to one degree or another, a very fine tremor, which is more marked if you hold something heavier in your hand. And the final thing to mention on this topic is what's called the TREP effect. So this is not how a muscle generates a graduated contraction, but it's a phenomenon that's demonstrated by all muscle fibers, and it occurs as follows. So imagine that the muscle is cold, so it's not been worked out at all. When it's initially stimulated, you get a release of calcium, and that causes the cross bridges to form in the muscle. And it only activates the skeletal muscle for about 10 milliseconds, whereas a muscle contraction takes about 100 milliseconds. Then the action potential decays and the calcium starts to flow back out of the muscle cell into the sarcoplasmic reticulum, and it relaxes. For a small period of time, if it is stimulated again, even during this relaxed state, it will contract with a greater force than before. And it does this mainly because, again, even when it's relaxed, for a short period of time, the muscle fiber cannot get all of its intracellular calcium back into the sarcoplasmic reticulum. So it has more intracellular calcium present, so it can create a greater force when another action potential arrives. This keeps happening up to about 25% of the maximal tension that you're able to develop in that muscle, assuming that you keep a regular interval between the contractions, say about 1 second. And this process looks effectively a little bit like a staircase, and that's why it's called the TREP effect, because that's German for stairs. And there are also other elements that are at play here, which is including changes to the ion gates and enzymes, which basically become more efficient with use. And some of the rising temperatures as well. And this is commonly referred to as what is the warming up process. So anybody that goes to the gym will know that when you first try to lift a heavy weight, you're not as good as if you first build up to that weight. So you acclimate yourself up to a heavy weight. So finally, let's put all of this together in the broader context of maintaining resting tone within our muscles and producing movements. At rest, we always have a degree of tone within the muscles, and this is due to weak and involuntary contractions or twitches of small groups of motor units in each muscle. This process is regulated by the brain and the spinal cord, which are always outputting action potentials. The muscles don't fatigue because the recruitment of small motor units is asynchronous, as we've previously noted, so it's constantly alternating between active and inactive, and this keeps our muscles in that kind of almost firm state. And it's important in skeletal muscles because it allows us to keep upright. For instance, you sit and don't really think about the muscles that are contracting, and you can keep your head upright without really thinking about it, and those muscles don't fatigue. It's also important in smooth muscles for digestion, and it's also important for things like maintaining our blood pressure. So this is an example of normal tone. But we also have hypotonicity and hypertonicity. So hypotonicity is where we lose tone and muscles are said to be flaccid. So you get hypertonicity in conditions that affect the peripheral nervous system. So i.e. if you physically damage a peripheral nerve, or if you get changes to electrolytes like calcium and sodium. But you can also have hypertonicity, where our muscles develop spasticity or rigidity, and this occurs in damage to our central nervous system, which basically causes a dysregulation of the maintenance of the tone peripherally. And we'll go into more detail about this in the neurological system physiology, but medically that's important to understand, because if you have a stroke or if you have any condition that affects the central nervous system, you're going to end up with high tone in the muscles. If you damage one of the peripheral nerves, then you will end up with low tone, and this is something that you can determine on physical examination. Finally, I'm just going to quickly mention the two movements that effectively our skeletal muscles can do. Firstly, they can do isotonic contractions, easily remembered if you think of gin and tonic. This is split into two parts. Concentric, which is where if enough force is generated in the muscle, in this case the biceps, that's trying to overcome the resistance, the weight of the object, then the muscle shortens and the structure, which is the forearm and the hand, moves, and it reduces the angle at the elbow joint, so that's flexion. Then the opposite way is eccentric contraction. So if the load, for instance, a dumbbell in your hand, is greater than the force which is generated by the muscle, then it lengthens despite contracting, and it does this in a controlled manner. And you'll notice how you can lower a dumbbell relatively slowly, assuming that it's not excessively heavy. The second type of contraction is called isometric contraction. That's where our muscle remains static, so there's no movement. And this is when the contraction and the load are of equal force. So the muscle is unable to shorten or lengthen, but it is still contracting. So that is isometric contraction and isotonic contraction. So that's everything that I wanted to go through in this tutorial. So to just quickly recap, we looked at the motor unit, we looked at how the motor neuron, the muscle fibers as a unit make that motor unit up. And if you have a small size and a large number of motor units, you get precision, and the reverse of that, you'll get more gross movements. We looked at the twitch contraction and how that's all about the single action potential, which develops that brief contraction. We looked at the types of muscle fiber, the type 1, type 2A, and type 2B muscle fibers. We then looked at quantal and frequency summation, remembering that quantal summation is all about the recruitment of motor units. And then we looked at frequency summation or wave summation. And then we looked at the slightly different types, the incomplete tetany, which is the way that most of our muscles contract, and complete tetany and Trett phenomenon. And we finished by looking at muscle tone and movement. We looked at normal tone, and then we saw hypertonicity, which is the effect of damaging the central nervous system. And then we looked at hypotonicity, which is what results if you damage the peripheral nervous system. And we finally finished by looking at the different types of contraction, the isotonic contraction and isometric contraction of our muscles. So thanks for listening. I hope you've enjoyed this episode. And if you have, please click the like button and subscribe to our channel. And we'll see you in the next one where we talk about cardiac muscle.